Hoor u mij? Is goed. Ouais.
Good evening, ladies and gentlemen. I would like to welcome you to the first public event of the International Space University Space Studies Program, hosted with the TU Delft, University Leiden, and the ESA ESTEC. My name is Omar Hatamli. I'm the Program Director and your Master of Ceremony today. I would like to thank the Netherlands Space Society, especially Dr. Gerard Blauw, who is currently chairing NVR and welcoming us tonight here at the Omniversum Theater. Thank you, Gerard. Just a few house rules. If you could please put your phone into silent. And just to make you aware, there is 2 emergency exits on your left here, and there's 2 on the back in case anything happens. After the event here, it should be about sometime, about 20 minutes, 25 minutes for questions and answers. And then we'll be showing a movie named Hubble. And then after that, also, Professor Hoffman will be available for meeting with you guys, taking pictures and so on. So since its launch, the Hubble Space Telescope has become one of the most extraordinary and beloved space science missions and has provided some of the most memorable images of the cosmos. But the telescope was not an immediate success. Without the work performed by STS-61 crew, including astronomer and NASA astronaut Professor Jeff Hoffman, the Hubble could have been a scientific disaster. You will hear tonight firsthand from Professor Hoffman. He will recall his shuttle experience as a space telescope repairman and discuss how those repairs have led to the telescope becoming one of the greatest science instruments ever built. Dr. Hoffman is actually professor of aerospace engineering at MIT Aeronautics and Astronautics Department. He received his PhD in astrophysics from Harvard University in 1971. As a NASA astronaut, he made 5 space flights, becoming the first astronaut to log 1,000 hours of space flight time across a space, aboard the space shuttle. Professor Hoffman is also the director of the Massachusetts Space Grants Consortium, responsible for space-related educational activities. So please welcome Professor Hoffman.
Well, thank you. Yeah, it sounds like the microphone is on. Thank you, Omar. Good evening, everyone. Sorry we're a little bit late. We seem to hit every red light on the way. But, you know, sometimes launches get delayed as well. But the important thing is that eventually you get into space, and eventually we get to give the talk tonight. So I hope the wait is worth it. So let me just start by reminding you that I'm not going to be telling you a suspense story tonight, okay? You know that we launched Hubble, it had a problem, We fixed it, and it went on to be NASA's most productive science mission ever. What I hope to do is to give you a little insight, first of all, into what actually went wrong. And I've talked with many astronomers who have, even people who have used the Hubble Space Telescope. And most astronomers know that, yeah, there was a problem with the big mirror. It was slightly the wrong shape. But very few people, it turns out, actually understand how NASA and the company that made the mirror could have made such a big mistake. And so after the talk tonight, hopefully you'll answer that. And then I'll go on to show you what it was actually like doing the mission that rescued the Hubble Space Telescope. But before we get into that, I think it's important just to remind ourselves, why do we want to put a telescope into space anyway? I mean, it's a lot more expensive to go into space than to build a telescope on the ground. And we have some very fine telescopes on the ground, and particularly these days with adaptive modern optics, you can get very clear views even through the atmosphere. But early in the space age, some far-thinking astronomers realized that if we could put a large, optically perfect telescope above the Earth's atmosphere, here you can see the atmosphere of the Earth, and the atmosphere is constantly moving around, and it distorts the images of stars and planets, galaxies. But more important, it also absorbs a lot of the radiation, ultraviolet radiation. Most of that doesn't get through. Good thing for us. Infrared radiation. If you go above the atmosphere, you have a much greater view of the entire electromagnetic spectrum and without the disturbance of the atmosphere. So the hope was that we would be able to get an unprecedentedly clear view of faraway galaxies to really understand the nature, the structure of the universe. This was the first part of the dream of the Hubble Space Telescope, but it didn't stop there. Hubble was going to be something totally unique. When you look at great telescopes on the ground, like the famous Palomar telescope, you build a mirror down here, that's the mirror of the telescope. Once you've built the mirror of a great telescope, it's good for decades. But you have to put observing instruments, cameras, photomultipliers, these days charge-coupled devices, at the focal plane of a telescope. And the technology of detectors advances very rapidly. It's sort of like Moore's law for computer memory. Every couple of years the capacity doubles. It's the same thing with telescope detectors. But up until Hubble, whenever we put a telescope, or for that matter, any satellite into space, whatever instrumentation was in that satellite when you launched it, that's what's going to be there for the rest of its life. Never mind if the technology evolves over the years, what you launch is what you get. Not with Hubble. The dream of the Hubble telescope was to make a telescope that could be serviced by astronauts in spacesuits working out of the space shuttle. And by the way, when Hubble telescope was first conceived, the space shuttle had not even flown, so it was a great leap of faith that we would even be able to do this. In order to achieve the optically perfect telescope, you have to have a mirror which is smooth to within a fraction of the wavelength of light. Just to give you an idea of what that meant, if this is the Hubble telescope mirror, and we did succeed in making it smooth to the specifications required. If this mirror were the size of the North American continent, 5,000 kilometers across in diameter, then the maximum deviation from smoothness could be no more than a few centimeters. That gives you a sense of how smooth it had to be. And if we were able to do this, and for some of you with a physics background, that means that in the wavelength of visible light, we would be able to get a resolution of about a 20th of an arc second, and in the ultraviolet even better. This was unprecedented. The technology that was used for the Hubble telescope was essentially the telescope technology of the mid-20th century. You start with a big piece of glass, just like the Palomar telescope. And then, just to give you, because you'll have to understand this in order to understand what happened to Hubble, when you actually grind away the surface of the telescope to make a curved surface that can focus, the easiest kind of figure to create is spherical. But the problem, if you have a spherical mirror, you have the light which hits the outside of the mirror is focused at a different point than the light that hits near the center of the mirror. This is called spherical aberration. In order to make a mirror which focuses all the light at the same point, you have to make what we call an aspherical mirror, slightly hyperbolic, parabolic type of a shape, so that all of the light, whether it falls on the outside of the mirror or the inside of the mirror, it's all focused at the same point. Once you do that, the basic way that the telescope works is there's a hole in the middle of the mirror, the light hits the big primary mirror, is reflected off a secondary mirror, through the primary mirror, and comes to a focus back here behind the main mirror. And then that's where you put all of your observing instruments, which have little mirrors which pick off some of that focused light. I'll show you detailed pictures of that later. Well, this was an unprecedented challenge. First of all, to make a large telescope that could be put into space that was optically perfect. That's hard enough. But to design it so that it can be serviced by astronauts, this is something that had never been done before. And as has often happened in the past, when you try to do something that is technologically totally new, you face a lot of challenges and you have to develop new technologies that you've never developed before. And the result is often that projects go over their budget and they slip behind the schedule. And sure enough, that happened with Hubble. And a lot of people don't remember this now, but there was a lot of criticism of the Hubble project because it was overcost and behind schedule. It's just part of life. You just have to kind of, I don't say you can ignore it, but you just have to persevere, get the job done, get the telescope ready to launch. And sure enough, in December of 1990, in the spring of 1990, the Space Shuttle Discovery did take the Hubble telescope up and put it into orbit. There was a lot of media coverage. It was very exciting. And the thing that was gratifying both to NASA and the astronomical community was that the public really responded, because the media explained how this great new telescope was going to open up the secrets of the universe, and we were going to be able to get unprecedentedly clear images of stars and galaxies, and all the secrets of the universe were going to be unlocked. Well, if you ever picked up a pair of binoculars, you know the first thing you do when you get a new pair of binoculars, you put it up to your eyes, you take the focusing ring, you sort of go back and forth, and you try to find the sweet spot in the middle where everything is in the best focus possible. And that's what you do with a new telescope, and that's what they did with Hubble. And they went back and forth and back and forth. And after a couple of weeks, it dawned on people that this was about as good as Hubble could focus. It was a real shock. This is a picture of a galaxy. When you looked at a star, this should have been just a point of light. Instead, the light was spread over a large area. Astronomers familiar with the laws of optics recognize this pattern as an indication of spherical aberration, which is what I showed you before. It was an incredible shock. Just to be a little bit technical about it, this is what the telescope was supposed to do. This is the radius in which a certain percentage of light should have fallen, and 90% of the light should have fallen within about 1/10 of an arc second. Instead, the light was spread over a much larger area, and that's what led to the problem with focusing. Now, those of you who were not alive and don't remember that time, it's hard to remember what a disaster this was, but it was a catastrophe for NASA, for the astronomical community. Hubble was denounced in the halls of the US Congress as a techno-turkey. NASA was the butt of jokes by late-night comedians. There was a movie, one of the airplane movies, in a scene in a bar, and they had the great disasters of history, and next to the Hindenburg was the Hubble Space Telescope. I mean, it was terrible. NASA at the time was trying to convince Congress to start funding plans for what eventually NASA wanted to become the International Space Station. As you can imagine, NASA was not very popular with Congress, so Congress's message to NASA was, you better do something about Hubble, then come talk to us about the space station. So what do you do when you have a disastrous problem? Well, in order to solve a problem, first of all, you have to understand what the problem is. So we formed what was called a Tiger team, a group of optical engineers, astronomers, astronauts. What happened? And this is the story I'm going to tell you that many people, even a lot of astronomers, as I said, are not familiar with. So you start out with a big piece of glass. And then, as I say, you have to make a curved surface on that glass to properly reflect the light, so you have to polish it. Now, it turns out, as I said, the easiest figure to put into a lens is spherical. And it also turns out that's the easiest shape to measure. You can use various types of interferometers. I won't go into the details, but you get these interference patterns, you get these nice straight lines, and you know that you have a good spherical surface. The problem, as I explained before, that the Hubble mirror was not going to be spherical because that gives you a spherical aberration. It has to be aspherical. And so what you do in order to measure the shape of the mirror is above the mirror, in the focal plane of the mirror, you put another small telescope, which we call a null corrector, and that actually makes the aspherical primary mirror look to the measuring instrument as though it were spherical, and then we can perform a lot of the standard tests, which, as I said, it's easy to measure the sphericity of a mirror. Now, this only works properly if you position this null corrector at exactly the right point, the right distance away from the mirror. And so in order to do that, in the middle of this null corrector, you put a measuring rod, or they call it a metering rod. And that has to be positioned very, very precisely in order to do the correction properly. Well, in order to make sure that we could do that, what they did was to put an end cap on the end of this metering rod, and there was, in the middle of that end cap, there was a little hole, and then you could shine, the top of that metering rod was reflective, and then you could shine a light down on it and measure the distance to that, measure the top of that metering rod, and that would assure you that you were in the right position. That's a picture of the metering rod. That's you can see the end cap on top of it. They call it a field cap here. And here it is installed in its position. And you can see once it's all installed and held up there, it's pretty hard to get access to it. Now they were worried. Potentially, what you don't want is for that little light to reflect off the top of the field cap. You want it to reflect off the top of the metering rod. And so what they did was to put an anti-reflective coating or non-reflective coating on the top of that field cap. So there's no way that the light was going to reflect off that field cap. It was only could reflect off the top of the metering rod. they went to the company in Connecticut where the mirror was made to look for the metering rod and the field cap, and they found it. It was stored off in a closet somewhere. It hadn't been looked at for a couple of years. And here's what they found, and sometimes you just get very unlucky. The anti-reflective coating, which is all over that entire field cap, right around that little hole where the light was supposed to go through, had peeled away. And so exactly what they were trying to prevent with that non-reflective coating is what actually happened. So this is what was, this is what was supposed to happen. The light was supposed to reflect off the end of the metering rod. Instead, it reflected off the end of the field cap, and the metering rod ended up about 1.3 millimeters too close to the mirror, which doesn't seem like a whole lot. But the net result was that the mirror was made slightly too flat. In other words, a little bit too much glass was removed from the outside of the mirror. How much? About 1 micron of extra glass was removed. The average human hair is 50 microns in diameter, so 1/50th of the diameter of a human hair was the error that caused the problem for Hubble. But the optics are so precise. They talked with the technician who installed that metering rod, and he said, "Oh yeah, I remember. I had a really hard time putting that in. I had to use several shims to get it in the right position." That should have been a red flag, and in fact, I can't go through the entire history, but all along there were several tests that were done that showed there might have been a problem. They were ignored for various reasons. There were all sorts of red flags which should have been raised during that time, but they never were. And so the net result was that the light was not focused at the same place, and you had classic spherical aberration. Once they realized what had caused the problem, then they could do a computer simulation to say, all right, let's assume that that metering rod was put 1.3 millimeters too low. What would the impact have been on the images? And you can see up there that the computer-generated images on the back look very similar to the actual images on the top. So finally, we felt that we understood what the problem was, and now hopefully you have an understanding of what caused that problem. So what can you do about it? Again, that's the basic form of the telescope. Remember that the light comes, it bounces off the primary mirror, off the secondary mirror, comes in here, and all of the different instruments have these little mirrors which reach out into the light that's coming down, which is now out of focus light, and reflect it into the servicing instruments. There were all sorts of suggestions. Change out the secondary mirror. That would have worked, but an astronaut in a spacesuit had no access to the secondary mirror. We needed some way that we, the astronauts at the time, we didn't know who the crew was going to be, but where astronauts could go up and actually use the serviceability of the telescope to actually fix it. And so they came up with a very clever solution. Instead of letting the out-of-focus light bounce off the mirror into the science instrument, and this is just a schematic, the actual thing was a lot more complicated, you had to, for every science instrument, you had to install 2 extra mirrors, each of them about the size of your thumbnail. The first mirror would block the out-of-focus light from getting into the science instrument. Instead, it would reflect it off a second mirror, which was slightly curved to compensate for the lack of curvature of the main mirror, and then it would be reflected into the science instrument. Now, Hubble's instruments were designed to be periodically removed and replaced by more advanced instruments. This is what the servicing was all about. This is what would keep Hubble as a modern science instrument. So if you're building a new instrument, you could actually put these corrective optics inside. And that's exactly, it had always been planned that we would have the first servicing mission in December of 1993, because the main camera on Hubble, the so-called wide field camera, was not as sensitive in the ultraviolet part of the spectrum as astronomers would like, and so they made the wide field planetary camera number 2, or WIFPIC 2 we called it. That was being manufactured at Jet Propulsion Laboratory, so they were able to install these corrective optics. And there you can see me holding the WIFPIC, and we actually took the old one out, put in the new one, which had corrective optics built in, and that took care of some of the problems. But there were 4 other scientific instruments in Hubble which were not planned to be repaired. How are we going to make them able to focus the light? We were going to have to put in a lot of these extra mirrors, and how are we going to do that? Well, each of those instruments is contained in a large box about the size of an old-fashioned telephone booth, the kind that you could actually get into. We don't have those anymore. When those instruments are installed into the Hubble telescope, you can't have anything hanging outside them. So somehow or other, all those mirrors had to be folded up inside this box. We would take out one of the science instruments, the photometer, which wasn't getting as much use as the other instruments, install this box with the corrective optics. And then once it was inside the shuttle, all those mirrors would have to come up and sort of open up like the leaves of a giant umbrella and all be put into exactly the right place to within a fraction of a millimeter of position. It was a very complex task, both from an optical point of view and a mechanical engineering point of view. Schematically, this is sort of the way it worked. All the mirrors were folded up inside that box. We put it inside, and then they come out and they essentially do their magic and correct the spherical aberration. Here's another schematic of a little bit more precise of one of the corrective optics for one of the instruments. And remember, there were 3 of those instruments, so we had a lot of those little mirrors. And they were all installed in what we called the Corrective Optics Space Telescope Axial Replacement, or COSTAR. And you can see up here, this is the hole under which all those mirrors are folded up inside. We had to put that inside the telescope, and then all those mirrors would come out. Over the years, remember, we've had 5 servicing missions. We were only the first one. And every servicing mission, they've typically would remove one of the old instruments and replace it with a new instrument with more up-to-date detectors, but also they could build in the corrective optics. And on the final servicing mission, the final old instrument was removed. It was replaced by a new instrument with the corrective optics built in, so they no longer needed what we had installed. That was removed, and you can now, if you visit the Smithsonian Aerospace Museum in Washington, D.C., you can see all of those little mirrors, the apparatus, what was designed. You can get some sense of how complex it all was. Okay, so where are we now? We believed that we understood what the problem was, how it was created. We believed that we had a solution. Now, from our point of view in the astronaut office, as you can imagine, this was a primo mission. I mean, everybody would have liked to have been on it. So who's going to get to be on the crew that goes to rescue Hubble? Remember what I was saying about the general tenor of the times. This was an absolute catastrophe for NASA. We had to get it right. We couldn't take any risk that something was going to get messed up. So NASA wanted to do everything possible to reduce the risk of failure. And one of the things they decided, because this was going to be the most complex spacewalking mission that NASA had ever done. there were, in addition to the corrective optics, there were a lot of other things that had gone wrong with Hubble. The solar panels weren't working right. Some of the tape recorders had failed. There were fuses which had to be replaced. All in all, there were about a dozen repairs that had to be made, and it was going to take 5 spacewalks. NASA had never done 5 spacewalks in a mission in the entire history. Even on Apollo, 3 was the most we had ever done. And so they decided only astronauts who had previously done spacewalks would be eligible to do the spacewalks for Hubble. And here's where sometimes luck plays a role in your career. On my very first space flight, that's our crew. God, I look young then. I can't believe it. Anyway, we were going to go on a mission. Basically, it was going to be a 4-day mission, the purpose of which was to launch 2 satellites into space. You can see that's the apogee kick motor, the perigee kick motor on the bottom of the shuttle, which after it leaves the shuttle, 45 minutes later, that motor fires to take, this is a telecommunications satellite, it's got to go up to geostationary orbit. The first one we deployed, it worked just fine. We deployed the second one, and you see that little antenna, that Omni antenna. After about 2 minutes, that antenna is supposed to pop up, which we had seen this happen many, many times in the simulator. And that would be an indication that the whole ignition sequence had started and that everything was going to work properly. Well, we deployed it, and I was looking out the window, and after about 4 or 5 minutes, it occurred to me that nothing has happened. That antenna has not popped up. So I called down to the ground, hey, Houston, we have a problem. The antenna hasn't popped up. Well, what could have gone wrong? We didn't have any special tools or anything on board to get inside and examine it, but it turns out there was one potential single point failure. There was a switch on the outside of the satellite. You can see it up here. When that satellite was inside the shuttle, that switch was depressed. That was part of the safety mechanism. That was part of the ignition sequence. You don't want the motor, the rocket motor, to fire when it's inside the shuttle. That would be a very bad day. So, as long as that switch is depressed, no ignition. The switch comes up, maybe the little micro switches underneath were sticky. So they came up with the one thing that we could possibly do would be we could make some special tools that we could attach to the end of the robotic arm. And this was kind of one of those, if you've seen Apollo 13, you remember that scene where they had to throw everything on the table and they said, all right, this is the stuff they have on board, now make this special kind of a tool. That's exactly what they did for us. Make a tool that they can use to flick that switch. And so, we sort of had fun and games on board for a day, cutting pieces of cardboard and plastic and hacksawing metal, and we put together some tools that we could actually attach. And what that meant, and I still remember that incredible moment when they called up and they said, well, we're coming up with several plans potentially for what you could do, and one of those plans involves a spacewalk. Now, 2 astronauts on every shuttle mission get trained in how to use a spacesuit just in case there's an emergency, but we weren't planning to do a spacewalk on our flight. And when we heard that magic word, spacewalk, my partner and I, what? Spacewalk? No, they're never going to let us go outside. I mean, NASA's never done an unplanned spacewalk. My wife was on the ground. She heard this. She called a friend back in Houston. They're not going to let him go outside, are they? No, don't worry, Barbara. There's no way they're going to let them go outside. But sure enough, out we went, and there we are attaching those 2 tools to the end of the arm. They look a bit like fly swatters, so we became known as the SWAT team. And then sure enough, we flew up to the satellite and we flicked the switch, and actually it turned out, if this had been a Hollywood movie, that would have solved the problem. It turned out that wasn't the problem, but it was still a very valuable thing because 3 months later, there was another crew going up, and they were going into an orbit which was compatible with visiting this satellite. Had we not done this, they would have gone up to flick the switch, because that was the obvious failure. It was the only what we call single point failure, and that's what you normally look for. Turned out there were multiple failures inside the satellite. They went up with special equipment, which we didn't have, so they were able to capture the satellite, open it up, and basically hot-wired it, and it finally did get up into geostationary orbit. The critical thing for me, I had my EVA union card, and so when they wanted EVA-trained astronauts for Hubble, I was fortunate enough to get onto the crew together with, let's see, my spacewalking partner was Story Musgrave, and the other two spacewalking team was Tom Akers, Kathy Thornton. We had our commander and co-pilot, and then Claude Nicollier, a European astronaut from Switzerland, was the chief robotic arm operator. So we're on the crew, we're all very excited, but now there's really intense training. Claude's training with the robotic arm. We were the first crew to introduce virtual reality as part of training, which is pretty standard procedure nowadays. But for spacewalkers, most of your training is underwater. We spent about 400 hours rehearsing every little thing because this was a time-critical mission. We had 5 spacewalks, a lot of things to accomplish. You could not afford to go out to do something and find out, oh gosh, I don't have the right tool. I got to go back to the airlock, get another tool, bring it out. I've just lost 20 minutes, which I can't afford. So we choreographed everything we were going to do to try to make our movements as efficient as possible. And as I said, 400 hours is a lot of time underwater. And the training was very intense. But finally in December, we got in our T-38s, flew out to the Kennedy Space Center. You can see our shuttle, the Endeavour, on the launch pad. The night before launch, spectacular. They roll back the protective structure so you can see the entire beautiful shuttle, gleaming white and lit up. And there happened to be a total eclipse of the moon that night, so it was pretty spectacular. And then we have that great moment. Let's see if I can get this to work. It's a lot noisier than you hear right now. You got to take my word for it. We call it riding the fire, and I mean the vibration, the noise, the power that you're on top of is just overwhelming. Takes about 8.5 minutes to get into orbit. Once we got into orbit, we didn't have a whole lot of time to look out the window and enjoy the beautiful view because we really had to get to work. The spacewalking team, the 4 of us, we had to get our spacesuits ready, and we had 4 spacesuits crammed into the airlock, which was normally designed just to take 2. So you can see it's very crowded in there. All of our critical equipment we protect from launch vibration by putting it in these foam boxes. Tools were absolutely critical for the success of this mission. We're working in big, bulky spacesuits with gloves that don't give you a whole lot of flexibility. Having the right tools for the job was absolutely essential. We carried about 200 different tools with us, about 100 of which we were planning to use, and the other 100 were essentially for contingency purposes. Several hours, one evening, checking out our spacesuits. Remember, your life depends on your spacesuit. It's got to provide pressurization, oxygen to breathe, thermal control, radio communication. You don't want to go out without being 105% sure that your spacesuit is in good operating condition. And so we check the inside, we check the batteries, the carbon dioxide scrubber, and then we're ready to go. So on a typical spacewalking day, I would get up early in the morning. I'd eat as big a breakfast as I could because I knew I wasn't going to get anything to eat for about the next 8 hours or so. And then the thermal conditions out there can be very extreme. When you're in the shadow, it can get very cold, And so you can see on my upper body there, I'm wearing thermal underwear, just like you'd wear on when you go skiing. But also when you're in the sun, it can get very hot. And so you can see I'm pulling on a second layer of long underwear, which is all through that, they run little plastic tubes where you circulate cold water. So you can sort of adjust the amount of cooling you have depending on whether you're in the sun or the shadow and how hard you're working. And then you have to get in the lower part, the trousers of the spacesuit. And by the way, in space, you can put your trousers on both legs at a time. You just float into it. That's kind of fun. Then you have to float into the airlock where the upper part of the spacesuit is attached to the wall. This is looking up into it. You can see the two arms here. The yellow material is the impermeable material, which holds the gas in. And then you have to slide in, which is a really tight fit. You can sort of see me squeezing there. And it's a really good feeling when you finally get up through. But the whole process is not over. We operate our spacesuits at about 0.3 of an atmosphere with just pure oxygen. And the reason we want to be at a low pressure is because a spacesuit is a little bit like an anthropomorphic balloon. And when you fill up a balloon, it gets stiff. And the higher the pressure, the stiffer your spacesuit would get. So in order to keep as much flexibility as we can, we don't put any nitrogen in the suit. We just use the minimum amount of gas. We have enough oxygen to breathe at about 0.3 of an atmosphere. Problem, if you go from sea level atmosphere to 0.3 of an atmosphere, you'll get decompression sickness, just like a scuba diver who comes up too fast. So what we have to do, we put on our helmet, we flow pure oxygen, we purge out all the nitrogen from the suit, and then we breathe pure oxygen for about 40 minutes in order to get enough nitrogen out of our bodies that we don't have to worry about getting the bends. And then we're ready to go to work. And I'm not going to show you the details of how we work on Hubble because we're all going to see the Hubble 3D movie at the end of this, and you'll see some great images, much better than I could show you. What I do want to share with you is some of the views that we had while we were outside. In this view, for instance, we had just installed the new wide field camera. This is the old one. You can see what we do. We take the old one out, we put it in temporary stowage here, we put the new one in, and then we have to wait for about 5 minutes. And on the ground, they check that all the connections are properly made, because if they're not, then we're going to have to take it out, put it in again. And if something goes wrong and it doesn't work at all, we would have had to take it out and put the old one back in. Once we got the old one, once it was clear that the new one was working properly, then we would take the old one, and you can see that's the thermally insulated box that the new one was launched in, and then we took the old one, we put it in the box, and we sealed it up and brought it home. You're working really, really intensely, very hard. But I have to admit, every once in a while, these moments come along, the sun is setting, and they'll call out to us, sunset in a minute, because we want to turn on our helmet lights so we can see. But you look over there, and you're flying over a mountain range, and the sun is setting, and it's just so beautiful. You just have to stop working for a minute or so and just take it all in. But not for too long, because we've got a lot of work to do. This is the image that we had of the Hubble telescope. It's really big. It's about 15 meters from top to bottom. And we were really fortunate. Our EVA team, we had to go up to the very top of the telescope on 2 occasions to service the magnetometers. And this was just an incredible, floating up there, 600 kilometers above the ground. You're suspended between heaven and earth, all alone. On this particular day, my partner Stories, his feet were locked into the end of the robotic arm, and I was what we call free floating. Both of us are attached to the shuttle with a stainless steel cable, but I was sort of holding on. And I'm enough of a physicist that I know I'm moving at the same velocity as the shuttle is, and so if I let go, I'm not going to go anywhere. I'll just float alongside the shuttle. So I thought to myself, I'm holding on, I'm floating. all right, I'm going to let go. And nothing happened. Come on, let go. Nothing happened. And I realized, there was something psychological. I just didn't want to let go. And finally I said, oh, come on, stupid, let go. So I did let go. And it was really amazing. I mean, it was, I didn't go floating away, of course. I just kept on in orbit next to the shuttle. But there was a psychological transformation. When you're holding on to the shuttle, it's so much more massive. You push and pull, and you're part of the whole shuttle system. As soon as I let go, I was a free-floating, independent satellite. Psychologically, it was amazing. And I kept doing that because it was so much fun. And what was greatest, at nighttime particularly, I like to sort of turn away from the shuttle and just look at the stars and the Earth, and it was like being lost in space. Pretty cool. Not a place if you suffer from vertigo. It's a long way down. Anyway, after our 5th spacewalk, we had actually replaced the corrective optics. We had put in new solar arrays. Everything that had been planned for us to do, we had managed to do. This was, as I said, the most complex spacewalking mission NASA had ever done. There were many people who thought it was too complex, that there was no way that we could get all these things accomplished. The one thing, so we felt very good. We had done our job. We came back home, big celebrations. What nobody knew, of course, would the corrective optics that we had installed actually do the job? Now, I'm not telling this as a suspense story. You know that it worked. But we didn't know that it worked at the time. And you can't turn the instruments on right away, because there's always a little bit of the Earth's atmosphere. Remember, they were on the Earth just a week ago, and there's a little bit of atmosphere that sticks to the surface, and you can't turn on the high voltage until all that atmosphere evaporates, or else you'll blow your high voltage circuitry. So we had to wait basically until the end of the month, and I'll never forget, this is one of those magical moments. As you know, has gone on to just produce these one after the other, these iconic images that everybody around the world has come to know and love. These, Pillars of Creation was one of the first, the birth of stars. I mean, it's almost biblical. Let there be light. And to celebrate the 25th anniversary, Hubble took yet another picture using the even more advanced camera. So this is the birth of stars. And then you have the death of stars, when a star uses up its fuel and blows off its atmosphere, not just in a simple spherical pattern, but these wild patterns that look like the work of some psychedelic artist. But it's not. It's the universe that we live in. And what Hubble has done, which is so great, is that they've made all of these images available free to anybody, anywhere in the world. I don't have a whole lot of time to talk about the scientific accomplishments of Hubble. I could talk all night about it, but I picked just a few of my very favorites, which I'll share with you, and then we'll have some time for questions, and then we'll get to see the Hubble movie. So the first is, astronomers now have discovered about several thousand planets going around other stars, but almost all of those detections have been indirect, either by occultations of the stars or by radial motion. But this one star, the Fomalhaut star, we actually were able to see. We have an image of the extrasolar planet that it's up here, and they followed it as it moved in an orbit around the star. So that's just incredible that you can see another star. Another thing which I think is really amazing, this goes back to Einstein's theory of relativity, that the gravity of a massive object like a galaxy or a group of galaxies can actually bend light and focus it like a lens. And that creates what they call these Einstein rings. So this ring that you see is actually the distorted image of a faraway galaxy that is focused by all of this massive galaxy in the middle. And by studying the nature of that ring, you can deduce the distribution of matter in the galaxy. And what this confirmed was something that astronomers had suspected for a long time. There's about 5 times as much matter in a typical galaxy as the stars that we can actually see. This is the so-called dark matter that you may have heard of. And then the famous deep field, where Hubble was exposed for 10 solid days to a part of the sky, sort of what you would see through a soda straw, which to other telescopes was empty, and there's thousands of galaxies there. So our concept of the number of galaxies in the known universe just went up by orders of magnitude. And of course, it was Edwin Hubble back in the early 20th century who was able to measure both the distance to galaxies and the speed with which they were moving towards us or away from us. And what he found was, by and large, most galaxies are moving away from us. And furthermore, the farther away they are, the faster away they're moving. It's as though a long time ago, the whole universe was very dense and it exploded in what we call a Big Bang, and everything has been moving out ever since. Astronomers have been trying to understand the overall geometric structure of the universe for many decades. It turns out that the farther away the galaxies you can study, the better you can do this. And Hubble, with its sensitivity, once we fixed it, was able to do this. And one of the critical jobs was to determine the rate at which this expansion of the universe was slowing down. Everybody knew, all astronomers knew, because of all the mass in the universe that has gravity, that the expansion of the universe must be slowing down because of all the gravity. There were two independent teams that were given the job to measure the rate at which the expansion was slowing down, and they didn't publish for a long time. Finally, they got together, compared their results, and the reason they hadn't published was because what they both found was so unbelievable that they were kind of afraid they had made a mistake. The expansion of the universe is not slowing down, it's accelerating against all physical intuition. There must be something else going on that is counteracting the gravity that should be slowing down the expansion, and we call that dark energy. You may have heard of it, and it's nice to give something a name because it makes it sound like you know what you're talking about. But in fact, we don't have a clue what dark energy is. But using various techniques with other satellites, you can measure what percentage of the universe is made of dark matter and dark energy and regular matter. And here's the very sobering result. It turns out that dark matter makes up almost a quarter of the universe. Dark energy makes up almost 3/4 of the universe. And we don't have a clue what they are. And so, with apologies to all of you students who have spent many years studying physics and chemistry and biology, everything that you've learned basically only applies to about 4% of the universe. Sorry about that. But that's what makes science exciting, isn't it? You know, you solve one problem and two more questions come up. And I'm just going to finish by, looking ahead towards the instrument. What happened to my image? It just went away. It was an image of the Webb Space Telescope. I don't know what happened to it. But in any case, no, it's not. All right, well, no, that's the mirror of it. I had a picture of an artist's conception in space. In any case, this is a telescope that's going to be much bigger than Hubble. It will be even more sensitive, and hopefully it may be able to solve some of these questions. That's all of the mirrors put together. This gives you some idea of how big the Webb Telescope is. It is huge. Those the solar shields, those big gray things, each of them are the size of a tennis court. This is so big that you can't launch it under the shroud of any existing rocket. So the whole thing has to be folded up. And it's not going to be orbiting the Earth. It's going to be put about 1 million miles away in the direction opposite the sun. And on its way out there, it's gradually going to have to unfold itself. And it's not designed to be serviceable because we don't have any way of servicing it out there. So we just have to hope that it works. Current launch is, again, it's such a complex mission that it's over budget, it's behind schedule. probably not going to be launched until sometime in 2020. But in the meantime, Hubble is going strong. Its discoveries continue. And one of the messages I'd like to leave you with is that the reason that the Hubble telescope has been so productive scientifically is because of servicing. You know, when people think about servicing the Hubble, I think most people think of the fact that we were able to fix the optics on the first mission. But remember, we have had 5 servicing missions, and every time they go up, they replace old instruments with new instruments with modern technology. When Hubble was launched, even if its optics had been perfect, it carried 1970s instrumentation. Now, Hubble is a 21st century satellite with almost 1,000 times the sensitivity of what it was launched with. That's the real value of servicing, and you're going to see some of that live in the movie, which most of the movie that you're going to see is about the 5th and final servicing mission. There is one scene, because we also carried an IMAX camera on our mission, and in the first scene, you'll see 2 of my colleagues out walking, and you may recognize my voice at one point. And of course, it was critical that we were able to fix the error in the mirror, but it was really the fact that we could continue to service Hubble, which is why it has been so incredibly powerful. So it's been a great story, and certainly a major part of what I consider, you know, one of the great satisfactions that I've had in life. Both originally, I was an astronomer by profession, and so both as an astronomer and an astronaut, to have been able to put my 2 hands on the great Hubble Space Telescope was the thrill of a lifetime. And I never get tired of talking about it, I have to say. If you notice that I seem to be enthusiastic when I talk about it, it's because every time I tell this story, and I have no idea how many times I've told it, but every time I tell it, it sort of takes me back, and that's why I love to talk about Hubble. And particularly if people are still interested in hearing about it, I'll keep talking about it, and I'll also be looking forward to answering your questions.
All right, so we're going to have time for questions. We're going to have people with microphones running around the aisles. If anybody has a question, please lift your arm and we'll get to you.
Professor Hoffman, thanks so much for your presentation. And
It was a pleasure.
It really does feel and hear anew, even if you told maybe dozens of hundreds of times.
Oh, we have a full house. Excuse me. It's always nice to know that people are still interested. That's great. Thank you all for coming.
Pertaining to the,
I'm going to move away here.
there's some feedback here. Does this work? Does this work? Can you hear me?
I can hear you. Yeah. I'll repeat your question.
Okay. So I got a question pertaining to the space shuttle. As a matter of fact, I was like 22, coming up to 23 when you went up into space, and I saw it live. We had just had CNN on our cable system here in Holland because of the Gulf War a year before, so I saw it.
Actually, I've been told by NASA that more people watched this Hubble mission than any other mission other than Apollo 11.
Yeah.
It really, there was a lot of attention.
Yeah, and I was too young for Apollo 11 anyways, but this was really fascinating and very inspiring. How do you feel about the demise and the cancellation of the whole space shuttle project and having it well, first of all, replaced by the Russians, of course, and now coming up with one-time use or limited reuse capsules? Because I thought that the space shuttle was very cool. It was like my whole life, my whole youth.
Yeah, I mean,
revolved around space.
the space shuttle was a remarkable vehicle. It was certainly the most versatile spacecraft that has ever been built, maybe that ever will be built. It's not clear that in the future we'll need something that's quite so versatile. Remember, the shuttle was 30 years old. I think the real tragedy is that we didn't have a replacement built when the shuttle was retired. We knew back in 2004, President George W. Bush announced that when the construction of the space station was finished, the shuttle would be retired. And in a sense, that it made sense. The shuttle was getting old. It was harder and harder to maintain, to fly safely. It was not inexpensive to fly. And to have continued to use the shuttle just to transport people back and forth to the space station, I think would have been extravagant given NASA's limited budget. But the fact that we weren't able to have a new replacement ready for it, I think is really a failure. And we're still working on it, but they're probably, hopefully, maybe next year we'll start flying U.S. astronauts in a U.S. spacecraft again, instead of having to launch them on the Russian Soyuz. Will we ever need something as big and versatile as the shuttle again? Maybe not, but the technology that we've learned about from the shuttle, hypersonic flight, thermal protection, the reliability of all the parts, the basic understanding of what's involved in reusing a spacecraft, all of these are legacies of the Hubble program. And of course, the greatest lasting legacies of the shuttle are the Hubble Space Telescope and the International Space Station, both of which would have been impossible without the shuttle.
Hello. Hi. First of all, as a cosmologist, I cannot thank you enough for being part of servicing the Great Hubble Telescope and allowing
Well, I
us.
can honestly say it was a pleasure.
I wanted to ask, when you were up there, or when you were preparing for the mission, do you ever expect the Hubble Space Telescope to be up there for so many years and giving us so much in science?
Well, that was the hope. I mean, that's why we made it serviceable, so that it would have a long life. And I have to say, when the final servicing mission, which you'll see in the movie, finished, they left Hubble as good as new. Hubble was kind of dying at that time. The batteries were at the end of their lifetime. The gyroscopes were failing. But they replaced just about everything. So not only does it have modern 21st century detecting instrument, it has new batteries, new gyroscopes, the whole works. When they left it in 2009, it was as good as new. And we've learned a lot about how to operate Hubble, keep the gyroscopes healthy. So, it could have a long lifetime ahead of us. We really don't know. It could fail tomorrow, or it could operate for another 10, 20 years. I hope at least that it will operate for quite a long time in conjunction with the Webb Telescope, because they are complementary, and that will even increase our ability to understand the universe that we live in. Another question?
Hi, thanks very much for your talk. I have a question about in-orbit servicing. Do you think that it's a kind of hot topic now? Do you think it would be possible to do the same maintenance on a Hubble telescope, but with totally automatic satellites?
Not on Hubble. Hubble was not designed for robotic servicing. I think because, remember, Hubble was designed back in the 1970s. We did not have the level of robotic technology that would have been capable of servicing Hubble. Hubble was designed for human servicing. I really think that when you're designing a spacecraft in the future for servicing, you should design it for robotic servicing. Actually, it's harder to design it for robotic servicing than for human servicing, because although we have very good robots, they're still not as clever and able to respond to contingencies and unplanned situations as humans. But if you design an interface that's simple enough so that a robot can do it, then if you run into any problem and you have to send a human to do the job, at least you've got a simpler interface to work with. So that I hope is the way things will work in the future. Many people, when they talk about, robots are so good, why do we need people to do things at all? I think they have a kind of a false concept of the level of robotics. They're thinking of R2-D2 and 3CPO and, that kind of level of robotic capabilities. And as good as some of our robots are, they're not that good. And there's still many things that people can do that robots can't do. And there are many things that robots can do that people don't have to do. There's no reason to send a human to do something that a robot could do. So let's design our servicing for robots, and then if something goes wrong and they can't do the job, we'll go and fix it.
Hi, thanks for this very fascinating presentation. It was very, very nice. You mentioned that you brought about 100 tools with you for contingencies, but considering the timeline, you had a lot of work to do. Did you actually have time for contingencies, or was everything so...
Oh, we had several contingencies. Several things did go wrong. I mean, on the very first job that we did, we changed out the gyroscopes, and then the doors wouldn't close. It took us about an hour to figure out what the problem was. We had to make an unorthodox use of one of our standard tools. We had to use it in an unplanned way in order to fix that problem. We had other problems. One of the solar panels, which we were supposed to fold up and bring back home, wouldn't fold up. We had to throw it away and leave it in orbit. Another device, they hadn't designed it for servicing, and so instead of having big bolts that you could work with spacesuit gloves on, it had tiny little 2mm screws, and we had to take all of those out, and they started floating around all over the place, and one of the screws got away, and we had to chase it. There were a lot of things that did go wrong, but we managed, despite all that, to get the job done. That's one of the things that a robot would not have been able to do.
Hello, thank you for your amazing talk. And I have a question. When you were a child, was your dream to be an astronaut?
Well, you know, when I was a little boy, I'm old enough, that was even before Sputnik, so my heroes were not the real astronauts when I was a little boy. They were the science fiction, you know, Flash Gordon and Buck Rogers and Tom Corbett, Space Cadet, and you know, some little boys played cowboys and Indians, but I played Space Cadet, and we shot each other with ray guns instead of bows and arrows and six-shooters. So I always, and then when we finally started flying in space, yeah, I was really excited, and I mean, all the little kids, well, especially the boys at that time, you know, now we have women astronauts, thank God. We didn't at first, but in any case, yeah, I thought it would be great to be an astronaut, but you know, it soon became clear that all of the astronauts back then were military test pilots, and that was not a career that I was interested in. And so I never really considered it as a realistic career goal. I was interested in space and astronomy, science and math in general, and I became an astronomer. And I was working at MIT in the mid-1970s, and that's when NASA was building and starting to get ready the preparations for flying of what was then the brand new space shuttle. And the great thing about the space shuttle was, well, many great things, but from my point of view, it had a crew of 7, and they only needed 2 pilots. And so that really opened up opportunities for scientists, engineers, medical doctors, people without military flight backgrounds to become astronauts. And that's when I started to think, hey, this would be a great thing to do. And that's when I applied, and I was lucky enough to get accepted.
Thank you very much for your story, sir, and sharing it. I must say I loved the message you sent about overcoming obstacles. I guess one can hardly deny that this is one of the greatest feats of astronautics ever. My question is, before you really let go for the first time, what was in your head? Why did you, in the end, let go of the spaceship?
Because I wanted to. No, quite seriously. I mean, I like new experiences, and I thought, hey, I have a chance to be a human satellite. And you know, when you're inside the satellite, inside the shuttle, you can float inside the shuttle, but you're sort of in, I mean, and it's a great feeling. I mean, just being weightless is an incredible feeling, even inside. But you go outside, and all of a sudden, first of all, the view out of a space helmet, the shuttle had good windows, but nothing like looking at a space helmet and, you know, you're surrounded half the world by the universe around you. And you know, also I'm an astronomer and I'm a physicist, so I understood the orbital mechanics. I knew I wasn't going to go floating away. You know, there's no wind out there that's going to blow you away. And so I just wanted to see what it felt like. And it was great, as I said. So I did it. It took a little convincing, but I did it.
Did you get reprimanded by NASA?
No, I wasn't doing anything dangerous. I was always attached to the shuttle by, yeah, we have safety tethers, but they're not pulling on me. You know, they were slack. So I wasn't going to go floating off into space. No, actually, just some people ask, you know, what would happen if you came untethered and you did float off into space? Then the shuttle would have to come and get me. That I would get reprimanded by NASA for sure. But didn't happen.
Thank you for your incredible story. One question. How did your wife react when she heard that you eventually got outside?
Well, you know, on the first time I did a spacewalk, on my first flight that was unplanned, I think I mentioned that you know, she was frightened, and she was hoping that they wouldn't let me do a spacewalk. It's not easy to be the wife or a husband of an astronaut. You know, I get to sit on top of a rocket and have a great ride and have all these great experiences. My wife has to worry about, am I going to come home alive? And you have to remember, you know, I was an active astronaut at the time of the Challenger accident. My second space flight would have been the very next flight after Challenger. So we knew the crew very well. That's not an easy thing for your family to deal with. And so, yeah, the husband and wives of astronauts, I think, deserve a lot of credit. Of course, her job was also to bring me back to Earth after the mission was over. So, you know, I got back from the Hubble mission, got back to Houston, came home, and my wife said, all right, Mr. Hubble repairman, while you were up fixing the Hubble Space Telescope, the washing machine broke, so get out your toolbox, see what you can do about it, and I fixed it. So, you know, you got to come back to Earth, and, you know, that's just the way it works.
Yeah, I've got a question for you right here. Right here.
Oh, yeah.
Yeah. Considering how incredible and complex the whole procedure was to repair and service the Hubble, why did NASA send a different crew? Almost, there was a rolling stock of crew almost, with Claude Nicollier coming again for the robotic arm. So why was there a rolling stock, and why was like the expert panel not there again and again and again doing the job?
Well, let me tell you what happened after the first Hubble mission. You know, we got back, and what our management said to us, you know, you guys had such a great deal being able to go up and service Hubble. We got to give a chance to other people to do it. So you're not going to get assigned to the next Hubble servicing mission. Now, we had numerous problems, as I mentioned, on our mission. The second mission went up, and they had a bunch of problems. The thermal protection was peeling off. They had various things go wrong. And it finally sunk in on NASA management that, you know, hey, servicing Hubble is really pretty difficult. We ought to start sending people up who have already been to Hubble so that we preserve the expertise. By that time, I had already left the astronaut office, so I didn't get to go again. But since that second mission, then they started reflying people. And so John Grunsfeld, actually, who you'll see in the next movie, he had 3 flights up to shuttle, and quite a few people had 2 flights. And I think that made good sense. I'm sorry they didn't make that decision after our flight, but that's the way. I can't complain. You know, I've had a great career. We had a great flight, and I did get one more flight after Hubble, although not to Hubble.
All right, last question. Just quickly, please.
Professor Hoffman, one final question regarding the EVAs, the extravehicular activities, spacewalks.
Spacewalk, yeah.
Yeah. Your colleague, the former or the late Bruce McCandless, was the first to use the
man maneuvering
yeah,
unit.
the jetpack, so
Right,
it's called
right.
MU. How come it wasn't used more often, and how come that you guys didn't use it for the servicing missions?
Okay, originally, the reason that this man maneuvering unit was developed, servicing satellites was always envisioned to be one of the important jobs of Hubble. And it was felt that if a satellite was turning, was revolving, that we wouldn't be able to grab it with the robotic arm. And therefore, you could use the man maneuvering unit to grab onto it, slow it down, and then we would be able to service it. Well, on the Solar Max mission, which was, I think, a little bit after Bruce McCandless made his first flight, they had a problem with the satellite. It was rotating, and they were able to grab it with the arm. You know, we practiced that in the simulators, and we showed that it could be done. And then, so the original need for the maneuvering unit was no longer there. And after the Challenger accident, NASA decided that every piece of equipment that we had needed to be recertified. And it would have been very expensive to recertify the man maneuvering unit. And so it was decided we didn't really, there was no demonstrated need for it, and so we never flew it again. Now, I mentioned that if I were to float away, get untied from the shuttle and start floating away, the shuttle could come and get me. We have a rule at NASA: for any catastrophic hazard, you need 2 independent safety methods of preventing that hazard. And obviously floating away and getting lost in space constitutes a catastrophic hazard, right? So we have 2 ways of preventing that. First of all, I have my safety tether, and if that fails, then the shuttle can come and get me. Now, step ahead to the space station era. We don't have a shuttle anymore. The space station can't fly and get an astronaut. So now, when astronauts do a spacewalk on the International Space Station, once again, they have a jetpack. But it's not meant for operational use like the man maneuvering was. It's only for use in emergencies. It has been tested. It works. We've never actually had to use it. But if you should come untied from the space station and start floating away, you can rescue yourself using your jetpack. So it's a kind of a mini man maneuvering unit.
Okay, to close the session, I think we have a question from Twitter.
The question is, how did astronauts protect themselves from small debris that floating outside, and how did they protect telescope lens from those debris?
Very good question, because space debris is a real problem. When we went up to the Hubble telescope, one of the first things we noticed was that there was a hole about 1 centimeter in diameter in one of the big high-gain antennas. Obviously, it had been hit by a piece of space debris. You have to remember, the space telescope was up there for several years, continuously. The space station has been up there for, 18 years. So it's been exposed to space debris for a much longer time. On a spacewalk, you're only going out for a few hours. So that's basic. There's nothing you can really do to protect yourself, except that your exposure time is limited. There is, inside the many layers in a spacesuit, there is one Kevlar layer which gives you a certain amount of protection against very small space debris. And then the other thing that we have is an emergency oxygen supply, very high pressure oxygen, which normally we don't use. But if your spacesuit gets a leak, like if you're hit by a piece of space debris and your spacesuit gets a hole in it, then that supplementary oxygen will open up and start feeding the leak to keep you alive. And it can feed a leak of almost a centimeter for about 30 minutes, which should give you enough time to get inside. So that's basically the only protection we have. It's always possible, you're out there and some big piece of debris with your number comes along, and You know, it's basically statistics, and so far, nobody's been hit. You never know. But it's a risk that, you know, there's lots of risks in spaceflight. If you're not willing to take a risk, you're never going to explore, you're never going to accomplish anything new. You have to make, everyone has to make a personal decision. Is the risk worth taking for the outcome, for the reward? And I certainly felt, given the importance of fixing the Hubble Space Telescope, I was willing to take any risk necessary to fix it. And as it turned out, it was definitely worth it. Thank you all.
Well, Jeff, really appreciate you taking the time to being with us this summer at the Space Studies Program 2018 in the Netherlands. And on behalf of the International Space University, we'd like to give you a small token of appreciation. And small globe. Yeah. Thank you very much. Okay, so we'll resume the movie The Hubble, and then there will be a small opportunity to meet up with Professor Hoffman here. Thank you.